day 3 notes, chapter 12, day 3 notes. This is your homework for over the weekend. You should come into class on Monday with these notes completed and your WISC completed as well. Our last set of notes finished up. We were talking about the size of ionic compounds. So we were discussing the fact that as a cation, as it loses electrons, and it becomes its cation, as the atom loses its electrons, comes the cation, it becomes smaller. And the anions work the opposite way. As they gain electrons, they become larger. So this is showing us what happens when you go from a neutral atom to a cation, and then from a neutral atom to an anion. You can see that they get bigger. So now we're going to be talking about that continuing. So here are some more examples showing you the radius of oxygen compared to oxide, fluorine compared to fluoride, lithium compared to the lithium ion, beryllium compared to its ions. You can see the differences and changes. So now we're going to put that to the test, and we're going to see if we can figure out which of these things would be smaller in the following pairs. Now, obviously, I'm not in class. If we were in class, I would have you guys try, raise your hand, and give me the answer as to which one you think it is. I encourage you to not just passively watch this video, but participate. Pause the video, decide what you think, which ones will be bigger or smaller, and then press play, and then I will show you which ones are bigger or smaller. So don't just passively watch this video, try and actively participate. You should be trying these examples on your own, pressing the play button, and then I will give you the answers. All right, so for example 1, we're supposed to circle the smaller ion. So we're looking for the smaller one in the pair. Remember, in terms of atoms in general, we can use our periodic table, and we know that things near fluorine are going to be smaller, and things towards francium will be larger. All right, so we know that fluorine and francium, those are the directions we're looking at. But now we have to take into consideration that we're not just looking at atoms, we're actually looking at ions. So, for example, we have calcium +2 or selenium 2-. So the first thing you do is you find calcium. So calcium is right here, and selenium is right here. Now, as they're atoms, calcium would be the larger of the two. But we're not dealing with regular calcium, we're dealing with calcium +2. So at the end of the last chapter, we discussed that ions become similar to the noble gas notation. So cations working backwards, anions working forward. So we would move backward 2 electron configurations. So we would move towards potassium and then back one more to argon. You guys might hear the drums telling Cole good luck. So this is the same as calcium 2+. All right. Then we have selenium. Selenium is Se2-, which means it goes forward 2 electrons. So instead of having 34 electrons, it has 36. It would match that of kryptons. This would be the same as selenium 2-. Its electron configuration would be the same. So it's not the same atom. Obviously, it has a different number of protons. But the thing that's determining that size, those electrons, the selenide ion would be larger than the calcium ion, because in these terms is where their ions are. Selenium is closer to francium and calcium is closer to fluorine. So therefore, the calcium ion would be the correct answer. It would be the smaller of the two. Now, these other ones are a little simpler, or the B and C are simpler. So rubidium or rubidium ion. Remember, if you lose electrons, that means you get smaller. So in this case, we lost electrons, making us smaller. And for C, bromine or bromide, if you gain electrons, that makes you bigger. So bromine would be smaller than bromide. For fluoride and oxygen, we have to do the same thing we were doing a second ago. So fluorine has a negative charge, making it similar to that of neon. And then oxygen also has a 2- charge, making it similar to neon. So they both end in the same spot. All right. Now, if they both end in the same spot, they both are landing in the same location at neon, then you base it off of just the regular atom. So then it's just fluorine or oxygen, which one is normally smaller, because their changes are the same. So whichever one is normally smaller is the smaller of the two. In this case, Fluorine is normally smaller, so it would be the correct answer. It's only based off of their original location if their new electron configuration takes them to the same spot. All right, so again, reminder, all elements want to be like the noble gases because they're more stable with exactly 8 electrons in their outer shell. Those are their valence electrons. Remember, metals lose electrons, become like the noble gas that was previous row, and then nonmetals gain electrons to become like the noble gas that was in the following row. That's what we saw happen here with calcium. Calcium became like argon in the row above it, whereas selenium became like the noble gas in front of it. All right, our example 2. Write the formula formed between each of the atoms. Name the noble gas that has the same electron configuration as each of the ions in the compounds. All right, so these are simply ionic compounds, nothing new, nothing we haven't done a million times before, going back to a little bit of old practice. So strontium, all right, strontium forms a positive 2 charge. We know this because it's in the second, that glare. It's in the second column right here, so strontium's right here, so that's a positive 2. So this forms positive 2. Phosphorus is in that negative 3, negative 1, negative 2, negative 3 row. So phosphorus is forming a negative 3 charge. Its formula we find by just crisscrossing those formulas. So this becomes SR3P2. Nothing new there. Now this next question is asking, what's the noble gas configuration for the ion of strontium? Well, here we have strontium. It forms a positive 2 charge, which means it's going to go backwards 2 spots. Back to 37, 1 spot, to 36, 2 spots, which means it has the same electron configuration as krypton. All right, phosphorus is here. It forms a negative 3, which means it goes forward 3 spots. So instead of having 15 electrons, it has 16, 17, 18 electrons. So it has the same noble gas notation as argon. All right. Make sure when I do these examples that you guys are, in fact, pausing, unpausing, so you can try them on your own. Don't just follow passively along, like I said. All right, sodium is in the first group. Alkali metals forms a positive 1 charge. Sulfur is in that second group. The chalcogens, that oxygen family, so it's that negative 2 charge. Crisscross our formulas, you get Na2S. All right, noble gas configuration. Sodium goes from having 11 electrons to having 10 electrons, which means it's the same as neon. And sulfur goes from having 16 electrons to having 18 electrons. So it's the same as argon. You're using those atomic numbers to help count your electrons. Good. All right, so a little bit left of today's notes. All right, so it says we've learned now how to write electron configurations for atoms. Now we can also write electron configurations for ions. It just changes however many electrons you have. Remember, again, this is like the second time. Remember, again, this is like the second time that this is in here. Metals lose to be like the noble gas before. Nonmetals gain to be like the noble gas after. So now we're going to write electron configurations, the full electron configurations for the atom and then for the ion. And then we would write the noble gas notation. Okay, so first one up is magnesium. It's right here. So if I'm writing out the electron configuration for magnesium, I start off with 1s2, 1s2, and then 2s2. Following across, I get 2p6, and then magnesium, 3s2. These electron configurations are not going away. For the ion configuration, you have to know what the ion is. Magnesium's in the second group right here, the alkali earth metals. So it forms a positive 2 charge, which means you're going backwards 2 electrons. So instead of having 12 electrons, it only has 10 electrons. Okay, you're removing 2 electrons. When you look at your electron configuration, you can see the 2 electrons I'm removing are these top 2 electrons. So the ion configuration is just 1s2 2s2, 2p6. The noble gas that has that configuration is the noble gas in the row above, which is right here, neon, 10 electrons. 2 plus 2 plus 6 is 10. Belongs to neon. This is no different than what we were doing last chapter. You're just moving over or forward or backward a couple of spots based off of the charges. All right, phosphorus is next. Phosphorus is right here. All right, so phosphorus ordinarily has 15 electrons, so we have to go through our electron configuration until we get to 15. So it starts off 1s2, 2s2, 2p6, 3s2, and then 3p3. All right. Now, phosphorus is in this group right here. It forms a -3 charge, -1, -2, -3. Phosphorus is going to form a -3 charge. -3 means it's gaining 3 electrons. So in this one, it was +2, so it was losing electrons. Here, now I'm gaining electrons. So I have to add 3 electrons to this last piece. So it would be the exact same configuration, except instead of 3p3, there'll now be 3p6. So 1s2, 2s2, 2p6, 3s2, 3p6. And 3p6 is the same as the configuration for argon. 15 plus 3 electrons gets me to the same electron configuration as argon. All right. That's it for tonight's notes. Make sure you go on, fill out your WISC. If you guys have any questions, bring them to class with you on Monday, and I will see you then. Have a good night.